So MALBEC feasibility of double stratospheric balloon observations. We made it. Okay, so you probably heard about the MALBEC project before. The idea actually came during the 2011 Draconids observation mission. So the idea is the following. Imagine that on the top left, you have a nice prediction of a meteor shower outburst. So you prepare yourself and you do everything so you can observe it. And on the bottom left, this shows the cloud coverage at the time of the outburst. Now you can clearly see that it's going to be tough to observe it. So what you can do is to basically have a mobile observation setup, and that's what Pedro showed yesterday with the two suitcases. However, in order to guarantee the observation of the outburst, what people have done in the past is to basically have an airplane observation campaign. This way, you guarantee that you're going to be above the clouds, and on top of that, you can actually relocate to wherever you want, especially in a geometry that allows the double station observation in nearly ideal conditions. So there has been a few stratospheric balloon observation of meteors, and the main advantage of stratospheric balloons is that they are much cheaper. You don't need a year or so to organize the campaign. Daniel Moser has done it, and some teams in Spain and Slovakia. So that was the idea of the MALBEC project. So MALBEC stands for Meteor Automated Light Balloon Experimental Camera. So the principle is to basically put two Meteor cameras above the cloud at stratospheric altitude. And the idea is that the observation happens during the ascending phase of the balloon. And for this, you will need two stabilized nacelles that would be coordinated in order to observe the same portion of atmosphere and perform double station observations. So why am I obsessed with double station observations? So this is more or less what Pedro showed yesterday. So you have the scientific goals in terms of meteor science, not only the science of meteoroids disintegration in the atmosphere, but also for the dynamics. So basically everything that happens before the events, and which is, as you know, our background in Paris. So what I'm really super interested in is the trajectory and the orbit, and accurate orbit. So for this, ideally, so of course there are many ways, one of them being the very method that you use to compute the orbit. But one thing to do is to have a double station observation for the triangulation. And you want sort of a narrow field of view camera. When I say narrow field of view, that would be like 40 or 60 degrees of field of view. I'm not going to go through the whole table, because most of you know all of that. Again, my point is that by using double station, my feeling is that you make the most out of any meteor observation, because there's so much more that you can study. And in particular, you can confirm the origin of the stream, you can look for parent bodies, you can study the age of the stream, and all of this would be quite hard with a single station. Okay, so on the left, you see one prototype of the MALBEC nacelle. This was presented by Athlin last year. And we have a whole model to basically compute and predict the trajectory of the balloon, and also the attitude of the balloon. So we can say, okay, the balloon should observe into that direction. And the main image in the center of the slide is basically a simulation of observation. So the two small yellow lines would be the line from the center of the field of view. So it basically goes from one nacelle to the center of the field of view at 100 kilometers of altitude. So you have two of them for double station. And so the yellow tiles would be the portion of atmosphere at 100 kilometers that is monitored by the two stations, and the blue by only one station. So in this case, what we want to check is basically how we can optimize such double station observations. So basically what we want to do is to increase this double station area. So the way we do it, instead of pointing the two nacelles towards each other, we introduce a shift in azimuth and also a tilt. So this is with a 20 degrees shift in azimuth and no roll tilt, so to speak. And if we add a 20 degrees tilt, then the area covered by the two cameras is now optimized. It's basically larger. Now, the next question is, how far can we go? Like, this is a simulation of an extreme case where basically we would observe almost 90 degrees from the direction of the other nacelle. And in such a case, the physical area is huge. Like, okay, we're talking about, we're located in southern France, and we could see up to Scotland. And the black tiles would be basically the portion of the field of view that is going to the ground. So basically, we would not see any meteor in those tiles. But then how is that possible? Like, would it really make sense to have such a setting? Because of course, the number of meteors that we're going to see will highly depend on the area that we cover. But then there are so many things happening. So what we would like to know is how many meteors will we detect from one camera and from double station cameras. So for this, I copied here the Holy rate, C as in camera, as a function of T. So that would be ZHR times time and sinus of the height of the radiant divided by the population index to the 6.5 minus the limiting magnitude of the camera. And all of these would have to be weighted by the physical area and compared to the naked eye area determined by Koschak and Rental in the 90s. But again, doing this, we actually need to take into account all the loss that comes when pointing a camera very low above the horizon. And I actually take this slide from the Meteorites 2019 conference. My point very quickly is to basically show that in the field of meteor science, anytime we perform simulation of possible observations, then we have some surprises. And apparently in the astrophysics world, so to speak, this is something that people actually do even before they build any camera, any system. For some reasons, in our small world of the meteor, we might tend to do the opposite sometimes. Again, the point is, every time we do this, of course, we have some surprises. Like, for example, computing the orbits of meteors is much harder to get if you want high accuracy than previously thought. Anyway, again, I'm not going to go through the whole table. Okay, so in order to answer the question, how many meteors we're going to see, so there are several factors that we are to compute. So the first is the air mass magnitude loss. So because of course, when you go very close to the horizon, the air mass is going to go crazy. So the magnitude loss is going to be high as well. But then you're stratospheric, so the magnitude, so the air mass is going to be reduced compared to the ground. So it's something to be taken into account. Then you have the distance magnitude loss. So basically 100 kilometers would be the ideal height or regular height of the meteors. But if you're 30 kilometers high, then you're only 60 kilometers from the meteor. So you would basically have a gain compared to ground-based observations. Then you have the apparent velocity magnitude loss. That is a function of the apparent velocity. And so I will show later that this actually depends on the geometry. So you would have the two exact same cameras, the same optics, the same computer, and so on, and still you would not see the same number of meteors just because of that, because of the difference of geometry. So you use all of these, and then you compute the area loss factor F, that is the population index to the difference magnitude that you would have compared to the ideal case. And then the total reduced area, you would compute this area loss factor for small tiles, and then you would add them up and multiply by the physical area. So if you want to know everything about that, you have all the reference. I mean, what I'm showing here is not new, it's been known. So here are a few examples. So on the top left, you would have the magnitude loss due to atmospheric extinction, so air mass. So so basically you see that when you go at 30,000 meters above the ground, then the influence of the air mass is not as strong anymore, and you can even go to negative elevation angle. On the bottom left, that's the influence of the apparent velocity, and basically when you're below 20 degrees, the area that you are sampling is so far away that the apparent velocity won't have any effect anymore. On the top right, this is the magnitude loss due to physical distance, and so this is basically the magnitude loss that you would have from let's say one flux at 100 kilometers, and what you would get at the altitude of the stratospheric nacelle. So you put all of these combined and so on, and you will have the reduced area versus elevation at the bottom right. So to show you one very extreme case, again, let's say you point the camera very low above the horizon, so all the black tiles are basically intercepting the Earth. And the point here is that, so red tiles would be high reduced area for 1 degree by 1 degree field of view. So the blue would be medium and the green low, so it's only qualitative here. And you can see that when you go close to the horizon, then your equivalent reduced area is low when the physical area is the largest. Okay, here's an example of what I mentioned before on the left. You can see the difference of reduced area due to the apparent velocity. And again, this is only due to geometry. Basically, one camera would see the meteors moving perpendicular to the field, to the line of sight, and the other one will not. So this will create a difference. And when you go to extreme cases, that's the graph on the right, then the reduced area would be the same for the two cameras, no matter what, basically because this is such an extreme case. Okay, now what I wanted to do is to have a comparison with real observations. And for this, so I talked with the Spanish team, and they pointed towards their video that are online, and they are available. So I encourage you to go and have a look. So Paco pointed to me a few video records, so namely number 89 and 94. And just by watching them, I could count about 12 meteors in a video of 1 minute and 45 seconds. So I did the calculation. So this was for the Jérémie 2016. So I took ZHR 120 per hour, took the population index from the IMO website, the characteristics of the cameras from Paco's paper, emitting magnitude. I put everything in there, and what I find is that my camera was supposed to see a bit more than 2 meteors in a 1 minute 45 seconds video. So there's a difference by a factor of 5, roughly, which is huge. Like a factor of 2 might be okay, but 5, I mean, I was shocked. And so there's something going on there. So I asked Zirko, okay, have you ever seen any difference? And he was like, well, yes, of course. So in his paper in 2017, from video cameras, his conclusion was ZHR was 350. So that's roughly, very roughly 3 times what the naked eye would see. So again, we did in there, and for Blau et al. For the Perseids, apparently in their paper, you know, the whole method works from for video observations compared to naked eye observations. I talked to Oriane, and she was like, in her paper, she had to introduce weights to compare ZR trough between visual camera and radio observations, and such comparisons are actually not as easy. And last but not least, so there was this paper recently by Richter, who basically was questioning the fact that the population index would be constant, or that the limiting magnitude of star would be the same as Meteor. So I have no answer to that right now. I'm just thinking that this is something to be digged in again. And you probably remember yesterday's talk by Jürgen Renter about the influence of the limiting magnitude and his role for observation for the coming Geminids. So conclusion, I believe we have showed that stratospheric double station observations are feasible, provided you have the right hardware. In a sense, the good news that our calculations tend to underestimate the number of meteors that's going to be expected, meaning that if we say we're going to observe 10 Geminids, we can expect like at least 20. And the next step for MALBEC will be to have a full fake-or double station simulation, basically to simulate the computation of, well, to simulate the observation from double station, and also to see how much we are able to compute the trajectory and the orbits. And of course, I would like to see some more real flights as soon as the COVID is leaving us alone. Okay, thank you very much.